Hello everyone, today we will learn about quadratic inequalities. Quadratic functions and univariate quadratic equations are topics we learned in junior school. Do you remember them? Let's first review the graphs and properties of quadratic functions. The graph of a quadratic function is a parabola, with the opening facing upwards when a is greater than 0 and downwards when a is less than 0. Parabolas all have axes of symmetry, and the equation is that x is equal to negative to a b. The number of intersections between a parabola and the x-axis is determined by the discriminant delta, which is equal to b minus for AC. When the delta is greater than 0, it corresponds to the blue parabola in the figure, and the parabola intersects with the x-axis at two different points. When delta equals 0, it corresponds to the black parabola in the figure, which has only one intersection with the x-axis. When delta is less than 0, it corresponds to the red parabola in the graph, which has no intersection with the x-axis. So, how to solve the abscissa of the intersection point between a quadratic function and the x-axis? Yes, we need to use the quadratic equation x, where the square of x plus bx plus c equals 0. The root of this equation is the horizontal axis of the intersection point, and of course, we need to discuss it on a case-by-case basis. When delta is greater than 0, the two unequal real roots of the equation are the horizontal coordinates of the two intersection points. When delta equals 0, the equation has two equal real roots, which are negative to a b, and this is the abscissa of the intersection point. When the delta is less than 0, the equation has no real roots and the image has no intersection with the x-axis. Next, I will give a definition, the 0 point of a quadratic function. For a quadratic function y equal to the square of x plus bx plus c, we call the real number x that makes the square of x plus bx plus c equal to 0 the 0 point of the quadratic function. So solving for the 0 point of a quadratic function is to find the horizontal axis of the intersection point between the graph of the quadratic function and the x-axis, that is, to find the real root of 0 for the square of the quadratic equation x plus bx plus c. So the case of the zeros of a quadratic function is exactly the same as the case of the roots of a quadratic equation. So, what is a quadratic inequality? It is also a member of our binary family, but it is an inequality. Before we delve deeper into it, let's first take a look at a practical problem. I have an open space at home, and based on its size, I bought a 24-meter long fence. I want to use this fence to enclose a rectangular nursery with an area of about 20 square meters. Let one side of the rectangle be a meters long. Please confirm which values the real number a can take. As shown in the picture, this is a 24-meter long fence. We have divided it into 4 sections to form a rectangle. So if we set one side as a, its neighboring side will naturally be 12 minus a, right? Can you convert the requirement of an area greater than 20 into an inequality? Yes, the area of a rectangle is calculated by multiplying its length by its width, so naturally it is a multiplied by 12 minus a. So the inequality is that multiplying a by 12 minus a is greater than 20. In practical problems, we must pay attention to the practical significance of unknowns, which often bring us some additional limitations. Here, a and 12 minus a both represent the length of the fence, so they are both positive. So a should be greater than 0 and less than 12. How do we solve this inequality? Let's first take a look at the formal characteristics of the inequality. On its left is the multiplication of factors a and 12 minus a. Students will definitely wonder, can we decompose 20? 20 can be decomposed into 4 times 5, 2 times 10, or 1 and 20. So, is there a fixed size relationship between a and 12 minus a and these numbers? Let's give it a try. It's not difficult to see that here, I take as 3, 4, and 6, and subtract a from 12 to obtain 9, 8, and 6, respectively. When plugged into the inequality, do they all hold true? So we can see that the value of a seems to have no fixed relationship with 4 and 5. Also, if we replace 20 with a score, will this method not be very effective? So we need to find a different approach here. Let's take a look again. You may have noticed earlier that a is greater than 0, and subtracting a from 12 is also greater than 0. Can we use this feature? Using the same solution principle. According to the principle of same solution of inequality, both sides can be divided by at the same time or divided by 12 minus a. The inequality can be transformed into the form of the following equation. We can see that the left side is already in a linear form, while the right side is in a fractional form. Can this inequality be solved? It seems a bit difficult, right? I still can't solve it. So from the above attempts, we can see that this inequality does not belong to a certain type of inequality we have learned, and cannot be solved using the methods we have learned before. So is it a quadratic inequality? Let's think back and forth. A univariate inequality only contains one unknown variable, so we call it univariate. Let's take a look at the form of this inequality. Does it only contain one unknown variable a? So it's also one yuan. Then let's take a look at the number of times. Remove the parentheses from the left equation and change it to 12a minus the square of a. Then move the left equation to the right so that the coefficient of the square of a becomes positive. The square of a minus 12a plus 20 is less than 0. The highest degree of the unknown variable a is the square of a, with a degree of 2. Therefore, according to the naming convention of equations and inequalities, we should call it a quadratic inequality. The following is the definition of a quadratic inequality. We call an inequality that contains only one unknown variable and has a maximum degree of 2, a quadratic inequality. Its general form is that the square of x plus bx plus c is greater than 0, or the square of x plus bx plus c is less than 0. Of course, we can also include two types of inequality, greater than or equal to or less than or equal to, where a, b, and c are constants and a is not equal to 0. In this practical problem, the general form of the quadratic inequality we are dealing with is that the square of a minus 12a plus 20 is less than 0. So how to solve it? Observing the form of the left-hand form, we can easily see that if a is replaced with x, what would everyone think? Yes, the quadratic function y is equal to the square of x minus 12x plus 20. Is there any connection between these two? If you still can't figure it out, why not switch to a linear function and a linear inequality? Have you been inspired by this? Firstly, if the square of a minus 12a plus 20 is less than 0, then the function value y of the quadratic function is less than 0. Secondly, solving an inequality means that when solving for the value of a, the square of a can be reduced by 12a plus 20 to be less than 0. Converting to a quadratic function means finding the value of the independent variable x that can make the function value y less than 0. Everyone will definitely think that now we should use the graph of quadratic functions. Come on, let's take a look at the picture. When x takes values within this range, the image is located below the x-axis, and the function values y are all less than 0. Obviously, this range is what we require. Moreover, we know that there are infinitely many values for x, and it is impossible to list them all. Therefore, in order to determine the range of x values, we must know the boundary values of this range. How to calculate the boundary value? Smart, you must have noticed that this boundary value happens to be the 0 point of the quadratic function. How to find 0? Yes, we need to rely on the quadratic equation the square of a minus 12a plus 20 to obtain the boundary values. The next step is to solve equations that we learned in junior high school. We calculate the discriminant delta to be 64, and then use the root formula to find two roots. One root is 2 and the other is 10, so its boundary values are 2 and 10. Then combined with the image, 2 is on the left and 10 is on the right, so we can obtain the solution set of the inequality as a greater than 2 and less than 10. Because it is a practical problem, we need to answer the question, the side length a of this rectangular nursery should be a real number greater than 2 and less than 10. Through this example, we have come into contact with a new type of inequality, the quadratic inequality, and we attempted to solve it using quadratic functions and univariate quadratic equations. Can you write your own quadratic inequality and solve it? Okay everyone, let's take a look. I have written two inequalities. Can you solve them? Let's first look at the first question. The square of x minus 5x plus 6 is greater than 0. What are its characteristics? Alas, not equal to greater than sign. So is the same principle used to solve the problem of unequal sign becoming greater than sign as before? Let's take a look at the first step. Let's still set a quadratic function y equal to x squared minus 5x plus 6, and then draw the image with attention to the opening direction, which is upward. Then, we require the boundary values of this region, which is to use the square of the quadratic equation x minus 5x plus 6 to solve for the 0 point of the quadratic function. Done! 0, 1 is 2, 1 is 3. Then let's take a look and see that it is greater than 0, so we should take the image of the part where y is greater than 0, which is the image above the x-axis. So the corresponding range of x values should be x greater than 3 or x less than 2, and then written in set form to obtain the solution set of the inequality. Next, let's take a look at the second question. What are the characteristics of the second question? It is not a standard general form. 2x is a linear term, and the negative square of x is a quadratic term. So we should first organize it into a general formula where negative x squared plus 2x plus 3 is less than 0. There are two ways to handle it next. The first way is to set the function y to be negative x squared plus 2x plus 3. When drawing, be sure to pay attention because the coefficient of x is negative, so the opening of the image here is facing downwards. Then we also need to solve for two zeros, assuming that the negative x squared plus 2x plus 3 equals 0. Solving for two zeros is negative 1 and 3. The inequality is less than 0, so the corresponding image should be below the x-axis. The corresponding range of x values should be x greater than 3 or x less than negative 1. So in this solution, there is actually a certain hidden danger of errors, because when you draw a function graph, you must pay attention to the opening direction of the function. So many students may feel it is quite cumbersome, and it is easy to overlook the opening direction when drawing. So can we make some improvements to the solution? Can we avoid ignoring the direction of the opening? Actually, it's possible. By utilizing the properties of inequalities, we can make the coefficients of x positive, that is, multiplying both sides of the inequality by negative 1 at the same time, so that the coefficient of x becomes positive 1. But at the same time, it should be noted that the inequality sign should become greater than the sign. So after this happens, let's assume that the quadratic function is y equal to x squared minus 2x minus 3, and its graph naturally has an upward opening. So solving the equation x squared minus 2x minus 3 equals 0, and we can obtain the same to zeros negative 1 and 3. Then at this point, the inequality is greater than 0, and the corresponding image should be the two parts above the x-axis. The range of x values corresponding to it should be x greater than 3 or x less than negative 1. Through the above two examples and the previous cited examples, we find that quadratic functions and quadratic equations play a crucial role in solving quadratic inequalities. To be precise, we observe the range of x values in the graph of a quadratic function, and then use a univariate quadratic equation to solve the boundary values of this range, thus completing the solution of the univariate quadratic inequality. Get an understanding set. It can be seen that quadratic functions, quadratic inequalities, and quadratic equations are closely related. Can you describe the relationship between these three in your own language? For each quadratic function, we can construct corresponding quadratic equations and inequalities, and the algebraic expressions on their left side are exactly the same as the analytical expressions of the function. From this perspective, the equation is actually solving for the value of the independent variable, where y will be equal to 0. An inequality is that when solving for the value of an independent variable, the function value y will be greater than or less than 0. The boundary value of the inequality solution set should be the 0 point of the quadratic function, which is the root of the one-variable quadratic equation. So, the combination of equations and inequalities solves the problem of the function values being positive, 0, or negative when the independent variables take different values. It can be seen that in the process of solving quadratic inequalities, it is natural to use quadratic functions, because quadratic functions are its essence. Next, let's summarize the general solution for quadratic inequalities of one variable. For general forms of quadratic inequalities, our first step is usually to set the quadratic function y equal to x squared plus bx plus c, draw its graph, and observe the direction of the opening. Of course, this step can be improved because in the case where the parabolic opening is downward, we can convert it to the case where the opening is upward by multiplying it by negative 1 on both sides of the inequality, but we need to pay attention to the sign change, so we can avoid the mistake of missing the direction of the opening. So when summarizing the general solution, we only need to summarize the situation where is greater than 0, which means the opening is upward. The second step is to obtain the 0 point of the quadratic function by solving a univariate quadratic equation. The quadratic functions mentioned in the previous questions all have two zeros, but in reality, there should be three possible 0 points for quadratic functions. When delta is greater than 0, there are two zeros. When delta is equal to 0, there is one 0. And when delta is less than 0, there is no 0. So for these three cases, what are the solution sets of this quadratic inequality? Can you write it down? Okay, let's work together to complete this table. The first line corresponds to three situations of the discriminant equation. The second line shows three graphs of the corresponding quadratic functions. The third line shows the solution of the corresponding quadratic equation. The fourth and fifth lines are the solution sets of two inequalities, respectively. Please fill in the blanks in the fourth and fifth lines. Let's first take a look at when the delta is greater than 0. At this point, the parabola intersects with the x-axis at 2 points, and the quadratic function has 2 zeros, which we denote as x1 and x2. Let x1 be less than x2. Therefore, the graph corresponding to the inequality greater than 0 is located above the x-axis. So the corresponding range of x values should be x less than x1 or x greater than x2. The range of x values corresponding to inequality less than 0 should be x greater than x1 and less than x2. Next, when delta equals 0, the parabola has only one intersection point with the x-axis, and the horizontal axis of the intersection point is negative to a b. That is to say, only when x equals negative to a b, y will be equal to 0. Otherwise, y is always greater than 0. So the solution set corresponding to an inequality greater than 0 should be x not equal to negative to a b. For an inequality less than 0, there is no corresponding image in the graph, so it should be an empty set. Finally, let's take a look at delta less than 0. When delta is less than 0, the parabola has no intersection with the x-axis, and the image is all above the x-axis. Y is always greater than 0. Therefore, we say that the solution set of inequalities greater than 0 should be all real numbers, while the solution set of inequalities less than 0 should be an empty set. From this, it can be seen that in the process of solving a quadratic inequality, the key point is to use the graph of a quadratic function. Everyone should never memorize it by rote, but must learn how to use graphs. Moving on to the practice session, these 2 questions are a bit more difficult. Can you solve them? Okay, let's start with the first question. 9x squared minus 6x plus 1 is greater than 0. We assume that the quadratic function y is equal to 9x squared minus 6x plus 1, and the image is open upwards. Let's calculate delta. Delta equals 36 minus 4 multiplied by 9 multiplied by 1 equals 0. This quadratic function has only one 0 point x equal to 1/3. Let's take a look at the graph. There is only one intersection point between the parabola and the x-axis where x equals 1/3, so the solution set greater than 0 should be x not equal to 1/3. Question 2. We assume that a quadratic function is y equal to x squared minus 2x plus 3, with its graph opening upwards. The discriminant is b squared minus 4ac, which is less than 0. Therefore, a quadratic function has no zeros. What do you want to write next? Do you want to write that the solution set is an empty set? You must pay attention to distinguishing between quadratic equations without solutions and quadratic functions without zeros. So, what is the solution set of a quadratic inequality? What are you going to do? On the graph, the graphs of quadratic functions are all located above the x-axis, so y is always greater than 0. Therefore, for inequalities greater than 0, its solution set should naturally be a set of real numbers, not an empty set. Review the process of solving quadratic inequalities. The process of solving an inequality actually involves using the graph of a function. You must have thought of something. Did we learn similar mathematical concepts in junior high school? Is there a similar relationship between 3 mathematical concepts? Can you think of it? It's just that it's not binary. Yes, linear functions, linear equations, and linear inequalities. The root of a linear equation is exactly the 0 point of a linear function, and when solving a linear inequality, we also use the graph of a linear function, right? Mathematics is truly amazing. Not only do functions, equations, and inequalities have their own systems, but there are also close connections between functions, equations, and inequalities of the same type. What does this mean? Mathematics is a whole, an impenetrable network with its complete and rigorous system. Finally, let's review the content of this lesson and ask students to think about the following questions. First, what is the relationship between quadratic functions, quadratic equations, and quadratic inequalities? Secondly, how to solve a quadratic inequality of one variable where the sum of x squared and bx plus c is greater than 0, or the sum of x squared and bx plus c is less than 0, where a is greater than 0.